In this last video on Kirchhoff's laws, we are going to put together what we've learned in terms of Kirchhoff's current law and Kirchhoff's voltage law and apply them to some circuits and more application wordy type questions. So let's see what we got. Example number 7. If we have two equal resistors along a path, what can be said about the voltage drops? For instance, find the voltage drop in the circuit below. So we know that we have the same current no matter where along the circuit we go. And our current and resistance and voltage are related by Ohm's law. So if the current is the same in both resistors, and the resistance is the same for both resistors, so these two things are the same, then that must mean my voltage drop has to be the same for both resistors. So if I have a total voltage gain of 30 volts, that means in order for each of this to give me a complete path around, I have to lose half of the voltage at each spot. So this must be a 15 volt drop, and this also must be a 15 volt drop. So if resistance is the same because of Ohm's law, and current is the same, our voltage drop must also be the same. If the resistances are not the same, then what can we say about the division of the voltage? For instance, compare the unknown voltage drops V1 and V2 below. So again, thinking V equals IR, but this time we don't have the same resistance. We have same current in both cases, but a big resistance, same current, big resistance is going to mean a big voltage drop. Can you see that? Current doesn't change. This gets bigger. That must mean this gets bigger. So big R, that must mean we had a big V1. Small r must mean a small V1. So if we're going to compare the two, that must mean V1 is less than, this is V2. V2 is less than V1. Last one, if the resistors are simple ratios of each other, we can relate the voltage drops via the same ratio. For instance, find the unknown voltage drops in the circuit to the right. Note the first resistor is twice the second. So again, thinking in terms of V equals IR, if R gets twice as big, V is proportional, so V is going to be twice as big. If R is half as big, V is going to be half as big. So 2R means we're going to lose twice the voltage here that we lose here. So this is going to be then 20 volts lost at the beginning and 10 volts lost the second one. 20 plus 10 gives me 30 volts lost total. All right, let's keep going. Although it's helpful at first to label the voltages at each point in the circuit like we have been, it is desirable at this point to label only the gains and drops. In all the following examples, the voltages written next to the resistors are understood to be voltage drops. They're no longer labeled drops, but they always at resistors will be voltage drops. Likewise, the voltage numbers written next to the cells are voltage gains. So if it's next to a cell, you know automatically this is a gain, not a drop. So for example, find the unknown voltage drops, currents, and resistances and power usages using V equals IR, P equals IV in each of these scenarios. So voltage drops, currents, resistances, power usages that were asked for. So we're going to find those things at every single resistor, whether they ask us for it or not. Those 4 things we're going to write down. So actually, this is V equals IR for resistance. This should have been P equals IV for power. You can figure that out. So we've got here at this resistor 4 amps and 6 volts. So if we have 4 amps here in the circuit, that 4 amps is going to split equally when it comes to this junction. So we've got 3 amps going this way. That must mean that only 1 amp makes it all the way around to this resistor. We know that a complete circuit, these 3 amps and 1 amp are going to come back together to give us 4 amps by the time we get back to the battery. And a complete circuit, a complete path, we have to lose all the voltage that we gain. So we've got 18 volts here. We lose 6, so that means we've still got 12. and go through this resistor. That's the only place we can lose the rest of it, so this must also be 12 volts. And same thing here, we've got 18 volts, lose 6. To get back to 0, we've got to lose 12 here as well. Parallel paths, same voltage drop, even though the current is different. And that current is different because of different resistances. So for that, we're going to use V equals IR, or actually R equals V over I. So here I've got voltage and current. So to figure out resistance, I need to take V over I, 6 over 4. So at this one, I got 6 over 4, which is going to end up being 1.5 ohms of resistance. At this one, again, V over I, so V over I, 12 over 3, this is only going to be 4 ohms of resistance. And last one, V over I, 12 over 1, this is going to be 12 ohms of resistance. So we can find the resistance using V over I, and then to find the power usage at each of these resistors, we're going to use P equals I times V. So this time it's I times V, so 4 times 6 is going to be 24 watts. 12 times 3 is going to be 36 watts. And 12 times 1 is going to be 12 watts. So you see how that works? We can use these formulas to find our missing resistance and power in each case. Let's take a look at letter B. I've got 35 volts coming out of my battery. Don't know how much current there is. 21 voltage drop here. So that's going to leave me with only 14 volts to keep going. Is that right? Yes, 14 volts to keep going. So making a complete circuit then, those 14 volts have to be lost in each path. To make a complete path, 21 plus 14 is going to give me my 35 volts total. To figure out the current here, I've got 1 amp and 1.5 amps leaving this junction. So that must mean total 2.5 amps went into that junction. So that 2.5 amps is also going to be the 2.5 amps that comes from the battery, either way that we're going in or out. Now to find the resistance, I'm going to use V over I. So voltage over current, 21 over 2.5, gives me a resistance of 8.4 ohms. V over I, 14 over 1, is going to give me a resistance of 14 ohms. And V over I, 14 over 1.5, is going to give me a resistance of 9.33 repeating ohms. And then I want to find the power at each resistor, so I times V, 21 times 2.5 is going to give me 52.5 watts. I've got I times V, 1 times 14 is going to be 14 watts. And 1.5 times 14 is going to give me 21 watts. So where you write each of those things isn't super important if you write them on the bottom or on the top. It's important to have the correct units, so it's easy to tell whether you're talking about current, resistance, voltage, or power. So you need to make sure you're including units so we know what we're talking about. A couple more examples. This time they are giving us some different things. So 40 ohms starts out, don't know what my current is, don't know what my voltage is, don't know what my resistance is, need to find all those. Okay, keep going. I've lost some, don't know how much. Coming around this path, I have 35 here, and I have to get back to the battery with 0. So if I lose 35 here, I must have lost the other 5 at this resistor. Otherwise, I couldn't get back with 0. And if I lose 5 here, I also, on the parallel path, must lose the other 35 in order to get back with 0. So parallel paths, same amount of voltage drop. And then I have 1 amp of current here, but I don't know how much current I have here. So I need to be able to calculate that using V equals IR, or in this case, I equals V over R. So that gives me 35 over 5 is 7. Whoops, let's try that again. 7.0 amps. So now I know I've got 7 amps here, 1 amp here. If I back that up, that must mean I had 8 amps at this resistor, which means I can use R equals V over I to calculate this resistance. So V over I, 5 over 8, gives me a resistance of 0.625 ohms. And the same thing here, I can use V over I, 35 over 1, this is going to be a lot bigger, 35 ohms. And I know this one already is 5 ohms. Then the only thing left for me to find is the power. So power equals current times voltage, so this is going to be 40 watts. Current times voltage, this is going to be 35 watts. And this one, again, current times voltage, 7 times 35, is going to give me 245 watts. All right, so I found everything for each resistor. If you feel like you're kind of getting the hang of this, why don't you pause your video now and then try part D and part E for yourself, and then come back and see how you did. All right, let's see what we got. We got 70 volts coming out of your battery and 5 amps flowing through this resistor. So 5 amps comes up to this junction, and then from there we don't know what happens to it. It kind of disappears. Well, not disappears, we don't have either of these to tell us what goes on. But we do have at this one voltage and resistance, so we can find current by voltage divided by resistance. So voltage divided by resistance, 15 over 5 is going to be 3 amps. So 3 amps out of our 5 amps came this way. That must mean the other 2 amps came this direction. And they all come back together here to give us, again, 5 amps. Then we can find the voltage drop here, because I know that voltage equals current times resistance. So this is going to be a 20 volt drop. So 20 volts lost here. And if I'm thinking now a complete path, I've got 70. Don't know how much I lose here, but I lose 15 here, and I lose 20 here. So 70 minus 15 minus 20 gives me a voltage drop here of 35. And this is in a parallel path to this one, so this must also be a 15 volt drop, so that if I go 35 plus 15 plus 20, I can get back to 70. A couple things left to find. I need the resistance here. So again, resistance equals voltage over current. So voltage over current, 35 over 5, is going to give me 7 ohms of resistance. And here, voltage over current is going to give me 7.5 ohms of resistance. Last thing we need to do is find the power in each spot. So power equals current times voltage. So 5 times 35, it's going to give me 175 watts of power. Current times voltage is going to give me 45 watts of power. And current times voltage is going to give me 30 watts over here. Current times voltage is going to give me 100 watts down here, and I'm done. Let's take a look at letter E. Starting out with 32 volts. Don't know how much I lose here, but I lose 8 here, and I need to have 0 by the time I get back to here. So 32 minus 8 means I've got to have 24 volts lost here. And 24 volts also needs to be lost in the parallel path. So that means if I lose 10 volts in the top path, or in the top resistor, I must lose the remaining 14 volts in the second resistor. See how that works so far? Then if we take a look at what's going on with our current, I've got 10 ohms of resistance here and 24 volts here. So to find current, it's going to be current equals voltage over resistance. So voltage over resistance, this is going to be 2.4 amps at this spot. I don't have two pieces of information here anywhere to be able to calculate the current here, but I do know that I have two pieces of information here to find the current. So voltage over resistance, this is going to be 4 amps. So I've got 4 amps coming out, and this is 2.4, so this must be the remaining. 4 minus 2.4 is 1.6. And that 1.6 has to go through both of these resistors. So to calculate resistance again, that's voltage over current. So voltage over current, 10 over 1.6 is going to be 6.25 ohms of resistance. And voltage over current, 14 over 1.6 is 8.75 ohms of resistance. Last but not least, the power. Current times voltage, this is going to be 32 watts. Current times voltage, 24 times 2.4, is going to be 57.6 watts. Current times voltage, 16 watts. And current times voltage, 1.6 times 14, 22.4 watts. So basically these questions are applying over and over and over again Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law, and then at the end, if you want to find the power, you can do P equals IV. Light bulbs are a good test of students' understanding of Kirchhoff's laws. The brightness of a light bulb is related to the power use in joules per second, and therefore depends on the current through the resistor and the voltage drop across the resistor. The higher the power, the brighter the bulb. The bulbs below are identical. They have the same resistance. Which bulb is brighter? So I've got 10 volts here. Each of these have the same resistance. Well, what do we know about the current in terms of the same resistance? We're going to have the same amount of current going both directions. So if this was I, this is going to be I over 2. Half the I go this way, and I over 2, half the I goes the other way. And these both have resistance R. So if I'm thinking, okay, and voltage, well, voltage is got to be the same no matter which path I take. So if I have 10 volts here, then I've got to lose 10 volts here and 10 volts here no matter which way I go so that I can get back to the battery with 0. So if I have the same voltage, I've got the same current, well, which bulb is brighter? Actually, they are both the same. Half the current goes through each bulb. Both of them have a voltage drop of 10 volts, so we're going to have the same brightness. Example number 10. The two bulbs below are identical. Which bulb is brighter? Again, identical, so same resistance in both cases. Since it's a series circuit, there's only one path. All the current is going to go through both of them. Since they're identical, we know that each of them uses up half the voltage. So this is going to be 5 volts and 5 volts. So again, the answer is both are the same. All right, that's it for this lesson. Have fun with your homework.